Good morning and welcome to yet another online Chai and Why. Today's topic is something that's pretty topical, face masks. But before that, let's just think about Chai and Why. And usually, we've had Chai and Why sessions on the first, third, and fifth Sundays. Oh, oops, what's going on? And the first Sunday session, well, we usually said that Chai and Why would happen always as scheduled, except if there were clashes with major festivals. We never thought that there'd be something called COVID-19 that would come and mess our schedule up. So we've gone online. And normally, on the first Sunday, we'd be at Prithvi Theatre. Prithvi Theatre, the wonderful Prithvi Theatre, and it's the Prithvi Cafe. And if you notice, the symbol of the Prithvi Festival is a mask. So it's a good time to talk about the science behind face masks, something that we are all used to using in this COVID world today. In case you want to sort of, wonder why are we doing this and who are we? Well, with me is Shankar, who is safely distanced somewhere in the room. We'll get him at some point. Now, first thing, Shankar and I are, physicists, engineers, call us what you'd want, but we are not medical professionals. So please, do post your questions on the YouTube chat or the Facebook comment section if you're watching us on Facebook or YouTube. And but we won't be able to answer anything about the disease, about treatment, about all that. We have no knowledge about the medical part of it. We're only going to talk about the physics and the science of masks and all kinds of masks. And in case you're going to, want to just a take-home message right now, well, there's actually an unbelievable amount of science that goes into even a simple mask like this or a much more complicated N95 mask like this. And, you must wear them correctly. That's one big message. That's what we will try and show you some examples of during the talk. And, for most of us, a simple cloth mask is good enough. Maybe a little surgical mask. You really don't need these N95s if you're at home. Healthcare workers certainly need much more protection, something like this. Okay, so let's get started. And, masks have been around for a very, 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 very long time, right? Since we've found traces of ancient civilizations, we found that they had masks. So the oldest mask is the one you see on your left. It's about 7,000 BC. It's a stone mask. And every civilization, every culture has had its masks. The Harappan civilization, the Mayans, this is tribes in North America, in Canada, what is Canada today, Africa, in India, we've had all kinds of masks. And masks have been used for various things to, disguise ourselves, to entertain ourselves, for various things, including protection. And protection from what? Well, even in the ancient days, the Inuit in the northern, the Eskimo region, they had to protect themselves from the sun. But we have to protect ourselves right now from something else, from pathogens, from virus, bacteria, etc. And even in the 17th century, when the plague was sort of devastating Europe, there was the plague doctor, and the plague doctor had to wear this bird-shaped, beak-shaped mask. And in those days, because they didn't know what happened, the word malaria, bad air, they actually tried to put in aromatic oils and things in this beak of the mask, thinking that would be actually what it is. But now we know that we need to filter. We need to filter out these things that we do not want to breathe in. And today, of course, we have masks used by doctors and nurses, the COVID warriors over here, and as well as all of us are using a mask or tying a dupatta, a handkerchief, something around our nose and mouth to help us breathe safely and also not transmit our own things, germs, which may be there on our exhaled air to others. So there are lots and lots and lots of masks, and I'm going to tell you a story today about how we got into all of this. Okay, so you see there are all these masks. There are what are called N95 masks, which look either like this, or sometimes they could be the flat fold, what are called the duckbill masks, which look like this. And there are these thin surgical masks, which have either little elastic straps that go around your ear, or you can sort of tie them behind your head. So these masks are all around. What's the difference between them? So the simplest thing, let's go to the CDC website, the Center for Diseases and Control, and they say, look, there are these two types of masks. On the left, you see what is called a surgical mask. And a surgical mask, they tell you, is designed to prevent and protect you from large size droplets. So if they are usually in a surgery, if the doctor had this on top of their nose and face. If something was going to splash during the surgery, they would be protected. But more important, they protect other people around from anything, large droplets which may be exhaled, either cough or things being breathed out by the person. So this thing helps a lot in preventing stuff coming out of you. It protects other people. Okay. On the other hand, a N95 mask, this is designed to filter very, very small particles. And this forms, of course, this is rather, there's a, it's not tight sealing. There's a leak at the sides from where the air gets breathed out. This one seals tightly against your face, and all the air you breathe in and out goes through this fabric, which filters very fine particles, and hence it protects you from breathing in these very fine particles. Okay. Now there is some level of confusion between these two, because to qualify a surgical mask, to qualify one of these, you measure how many bacteria of 3 micron size get through the mask, right? What percentage does it block? It needs to block 95% of them. On the other hand, for these masks, you need to measure a much smaller size, 0.3 microns. And this actually causes thing, and of course it depends on how you fit and all that. But wait, I said I'm going to tell you a story. And this sounds like I'm giving a talk and not telling you a story. So I should be telling you a story. And like any good story, let's start at the beginning, because this is actually a very interesting and fun story of the last 3 months. So let me continue with the story. And the story obviously begins with the lockdown. They announced the lockdown. And well, we all thought, what are we going to do in the lockdown? I thought this was a great chance. I will catch up on some reading. I will catch up on some writing. Enjoy a little bit of there won't be pressure of the lab so much. And yes, the first day I did go out and, looked at all the birds outside my window, which I normally wouldn't have the time to do. But very soon we got caught into making sanitizer, and you see the sort of another of my standard chai and Y people, Mr. Kulkarni. With him, we made a lot of sanitizer for the staff at TIFR. By now, we've probably made 500 or 1,000 liters, perhaps, who knows. So we've been doing this, and I thought, okay, that's fine. Well, on April 3rd, we got asked, would we be willing to work on something related to masks and decontamination of masks? Now, for me, masks meant only one thing. Masks are something I've used for the last 20 years in my research. Masks are something you use when you manufacture semiconductor devices. And in fact, the first thing I did exactly 20 years ago when I joined as a postdoc was to make a shadow mask to make laser diodes. I said, yeah, okay, masks. I know something about masks. I didn't realize that these were completely different masks. Shankar, on the other hand, had no clue about masks. But he read a little bit and he found, wow, there's probably some cool physics in it. So we said, fine, let's do something. Let's work on masks. Okay, but what are we going to do? The idea people wanted us to see, how do you test if a mask is actually filtering the particles that it's supposed to be filtering? You need to make a mask tester. We looked around and, well, they are commercially available and they are, humongously expensive. They cost over 20 lakhs. And a lot of people around are going to, wanting to build masks to get this COVID epidemic. There's a shortage of masks everywhere. We read reports, everything. So there are a lot of materials. You need to test the materials. And, people were buying masks and they didn't know whether they're good or bad, hospitals in particular. So how do we help out? So, well, we had to get people who are around. And in the first part of the story, it's mostly the students who were stuck on campus, couldn't go home. We got them to say, well, can you please help us? We need to work on masks? And we assembled a little team. And as you'll see later in the talk, there's an Act 2 and an Act 3, and more players have come in, including Dove from Technion in Israel. Okay, so on 9th April, we figured out that yes, we can actually do this. We can do this, and we have a clean room at TIFR. I went and took the clean rooms. There has it monitors how clean is your clean room, is how many particles are there. So we could use the same device to measure how many particles are going through a mask. So we did this with a clean room, and we had at least one way of knowing that yes, we can test this. And we tested all the materials that we could lay our hands on in the lab. And yes, we had the first thing that we could do. But this, of course, is not very practical to deploy it everywhere. I had been looking around and thinking that there were other groups, other volunteers around the world who were doing it. And in the next few days, a lot of interesting things happened. So on the 9th, I wrote to an international consortium headed by Manu Prakash at Stanford called N95 Decon for decontamination. And I said, can I at least, join your team? Can I listen to what you're doing? Can I access what your documents they have? And it's amazing. I sent a mail at 6:23 in the morning, and immediately I got a reply within a few minutes saying that yes, we can include you in the community. By some time, I had got Shankar added as well, and within almost an hour, we were on their Slack group. And that evening, I could attend one of their seminars, which were happening at 8:30 p.m. that day on low-cost testing for low and middle-income countries, etc. And I learned a lot of interesting things over there. And I figured out that you could use pollution monitoring devices that were around. Meanwhile, on the 10th morning, again, it's just amazing what you can do with WhatsApp these days. I got a message from the director of the Tata Memorial Hospital. Again, luckily I was online, sent at 9:34, and by 10 o'clock we had a meeting. And given that yesterday we had got this data, I was really upbeat about, yes, we should be able to do something. And I'd heard that there are low-cost solutions. So I said, yes, I'll do something, not knowing what we'll do. Okay, so now we've committed to helping Tata Memorial Hospital measure filtration efficiency. We'll build some gizmo, but we need these particle counters. We can't use our clean room counter all the time. And I Googled who sells this in Mumbai, the standard places in Lamington Road where you get electronics, or Loharchal where you get electrical supplies. Everything's closed. So I start just cold calling people from a Google list, India Mart, whoever makes pollution monitoring equipment. Do you have a sensor like this? And mostly wherever people picked up, sorry, we are closed, or we don't do 1 or 2 pieces. We can import 100 pieces for you, but it will take time. And then the fourth person I called, Ronak Sutaria, company Respire Living Sciences, no idea whom they are. I explained that I'm from TIFR, I'm trying to do something, and guess what he says? He tells me, yes, I know you're Arnab from Chai and Y. Tell me what you want. Amazing, Chai and Y. I never thought it would ever help me like this. But we got Ronak on board. Very soon, we arranged for a pass for him, dragged him out of his house, got him to get these devices from his factory, brought him to TIFR, and that evening we worked in the lab pretty much late night, and we had something that worked. So initially we were trying on the 10th to make some experiments in the lab, but by the 11th, once we had got this little box, we had an idea of what to do. And as you can see, this is all built during the lockdown, made from toys, made from plastic dabbas, whatever we could find at home, vacuum cleaners, etc. And we had, of course, improved this setup a lot. And by 12th April, we actually had a prototype where we could put a mask on it and make some measurements. Okay, but don't worry, we'll have to tell you what is happening. So picture baki hai, don't go away. We'll fill you in on the details. Now, if you want to, what's there in this? When's he going to come to the physics? Well, we are going to come to it, but it's been an amazing journey. Once we made this little tester, not only did Ronak and this company, so on the 12th we had a prototype. On the 14th we could submit a thing to the MHRD for a startup competition, and very soon after, the next week, to the DST. And he actually got funding support to build prototypes of this. We've been in touch with other companies who've been sending us materials to test for masks. And of course, we've been working very closely with Tata Memorial Hospital, measuring all their masks. And it's unbelievable. People are willing to donate supplies of masks and all, but they have no way of knowing if the mask is good or not unless you have some way of measuring it. And this simple thing that we've done actually can help you measure the mask. But there's more. We've also got some very cool ideas of a sort of, you can say, a battery operated mask. More about this later, but it's fun stuff. So let's actually get back to the topic, which was the really cool physics of how masks work. And for this, I'd like to invite my partner in crime, Shankar Ghosh. Shankar knows all about the physics of matter in everyday life. He works on what is called soft matter, as he says, matter that matters in everyday life. So he plays around with, how things stick, how things peel off, how things, friction, lots of fun things that happen every day. And he found masks were equally exciting. So let's get Shankar on. Shankar, let's get you on here, and he takes over for a while.
Thank you, Arnab. Well, this has been 3 very eventful months for us. As a researcher, you often, once you've finished your PhD and have become a faculty, you often lose touch of doing experiments on a day-to-day basis. This is something that you do in your graduate or postgraduate days. Uh, so this 3 months gave me a chance to look back, do these experiments, build up prototypes, and enjoy my time there. And in this whole process, I learned a lot about masks and the physics behind masks. So I will basically run you through it. So what is a mask? So well, a mask is something that filters out toxic particles, whatever your definition of toxic particles could be. If you are in Delhi during the winters, well, some particulate matter, which is because of burning of some farm stock, could be your toxic particles, and that's something that you want to filter out. Okay, but there's no point in having a mask through which you cannot breathe. So essentially, you need to have something which is breathable. And this is at some level, it's in contradiction to each other, because if the particles are small, you want pore size to be small. And if the pore sizes are very small in your mask, then you won't be able to breathe. So there is a trade-off. And the whole idea is, how do I stop particles of a given size, but nevertheless be able to breathe from it? If I could do that, then that's the best mask. So typically, like, if you want to filter out particles, the first thing that comes to somebody's mind is basically a sieve. Okay, this is a picture which all of us have seen. This is from the construction site. And what you basically have is a sieve which has small holes in it, and you kind of throw your sand at it, and the right side size sand, which is smaller than the sieve size, passes through, the other sand falls back, right? So essentially what you get on the other side is a finer sand. Okay, so essentially what you say is, all the big particles have been blocked, all the small particles have passed through. So essentially what you have is, if you look at this picture, then you have, say, this is my filter material. This has a length scale, say L, in it, and I will have some particles up here. I'll throw these particles at this, and some particles will go through and some particles will not. Now, if you had spheres, then it would be easy, right? Because what you do is, you have only one length scale associated with the sphere. So for example, let me think of a sphere whose diameter is A. And let me think that, all these sieves that I showed you had squares of length L. And if L was to be smaller than my diameter of the sphere, then this particle would get blocked. However, you could have objects which are like this, or like that, or like this. If you have objects like this, then you don't have one length scale in your problem, you have multiple length scales in your problem. In 2-dimension, this obviously has two length scales. This has a major axis, which is like this, and a minor axis, which is a thinner axis. So if this thinner axis is smaller than your length scale in your system, so this is the L, this is your sieve size, and if this scale is smaller than the sieve scale, then this particle will go through. So essentially, if you have to build up a sieve, then you want the scale of the sieve to be smaller than the smallest length scale that you have in your system. Now that's something to worry about. And let me go to the next slide. And this is some game that I can actually play with you, and to drive the point. Arnab, is it possible to actually turn it and so that I can do it on the board?
Yeah, sure.
Let's start on the board. So let me think that I have actually got 3 coins, and you can actually think of 3 coins. And these 3 coins are kept in such a way that basically touching each other. So this is a 1 rupee coin, this is a 1 rupee coin, this is a 1 rupee coin. And now, if I ask you, what is the length scale in this problem, you would say, well, now for the coins, so let me shade the coins. This has a length scale, say A. Okay, so the length scale, the diameter of each coin is A. Okay. Why do I say this is a length scale? Because this is one scale by which I can actually describe these coins, these 3 coins. It's a 2-dimensional problem. Now, if I were to go and ask you this question, that these are your blocking particles. This is the part of the metal wire in your mesh. what is the length scale associated with the pore. Now this part is the length scale that is associated with the pore. Now this turns out to be tricky because you look at it, I can't fit one length scale into the problem. How do I fit length scale? The way I fit length scales is, let me rub it up here, and this you can see. The way you fit length scales is to say that what is the right length scale of a circle that I can fit in. Well, I can fit in one circle like this here, but then this is left part back. So essentially, I'll go back and fit smaller circles like this, right? So there's another length scale in the problem. Then I can go and fit in still smaller circles up here, and so I can get smaller circles and smaller circles.
Use some other color.
So essentially, while these things have a nice length scale associated with it, this pore size, the pore space, do not have very good length scales associated with it. In fact, they have distribution of length scales. And this turns out to be a problem in filtration of particles. Because what you want is the smallest length scale here should be smaller than the length scale associated with a particle. So essentially, if I have a particle like this, and this is the smallest length scale associated with this particle, say this is the,
come on this side, come on this side.
Suppose let me take this object, this is the smallest length scale associated with this particle, then this length scale should be smaller, this length scale should be smaller than this length scale. And only then will I be able to block it. So this is one thing that one has to keep in mind while you're filtering particles, that while the fibers themselves which make the mask actually have a length scale associated with them, the pores that you have inside do not have a characteristic length scale associated with them. And in addition to this, you also realize that this is kind of a simplistic picture of what you have for masks, because your masks are not necessarily two-dimensional. If you look at any of these masks that you have, then this mask is actually three-dimensional. There's a thickness to it, right? So essentially what you have is you have a particle. This is not a picture of a mask, but anyway, you can get the point that I have a particle which enters from this point. So I have a particle which enters from here and it goes out from the other side here. And essentially there is a very tortuous path through this which the particle has to go. The longer the particle spends in this tortuous path, the chances that this particle will hit to a surface, which is a fiber up here, and get stuck increases. So what you want is, you want the gaps between these fibers to be large, but you want the circumstances to be such that there is a chance that this particle goes and hits to the surface, and for reasons which I will explain later, that this particle now gets absorbed to the surface of your fibers. Okay. So essentially this is a problem, that you have a fiber on which you want to get this particle stuck. So this particle comes and sticks. But there is also a problem that because you're breathing through it, you're kind of pushing air through it. You also have this problem of this particles detached. So imagine that you're wearing this mask for about, say, the whole day, and it's basically collecting all your dust that is on this mask. But as you breathe in and out, you also dislodge these particles from the fibers, and there's every possibility that you are also ingesting. This is a secondary ingestion of the particles that you get to your face. Okay, so this is one reason why they say that don't use one mask for a very long period of time. Wash it. If you're using a handkerchief as a mask, or if you're using something of this sort, change it. Do something of that sort. Decontaminate your mask, which Arnab will tell you more about. So why not use a very fine mask? The reason is that if you use a very fine mask, typically we exhale and inhale about a half a liter of your gases. And if you use a very fine mask, then you won't be able to inhale and exhale that amount of gas. So essentially, if you don't inhale and exhale, your lungs are not strong enough that it's going to suck in that amount of air through this large impedance path, which is provided by your mask. So essentially, if you don't do that, then you will start feeling breathlessness and things like that. So you will be short of breath. So how do these particles stick to the surfaces? Okay, one way is very simple. The particle comes, it finds a fiber in its path, and then hits it across the fiber, and then because of some interactions gets stuck to the fiber. This is almost like a footballer who is taking a penalty shot, hits the bar post, okay, or that's what it does. So essentially that's one way. The second way is, so these are lines that you see. There is this fiber up here. I'm doing a cross section of the fiber, And there are flow lines which are passing through the fibers. These flow lines are basically, if I had taken very light particles, almost massless particles, and I've left it there, then this particles would actually flow along this particular lines that you have. But these are not tiny particles that you want to filter. They are inertia, and this is exactly what happens to this car. When you try to bend through it, you don't bend along the line, but you kind of overshoot it. If you overshoot it, then sometimes this path, if it was very small, the particle would have gone and passed this fiber. But if you overshoot it, you go and crash against the obstacle, and this is what happens. You're going to crash against this object, and if you crash against this object, which is a fiber, then you have a chance that this fiber is going to trap your particle. The third process is, because there's temperature and since these particles are small, they kind of do a Brownian motion. Brownian motion is some random motion. This randomness comes because of temperature, because of wind fluctuations, because of various things in your system. And because you have fluctuations in your system, then essentially it doesn't follow the trajectory, but kind of meanders about the trajectory. And the extent to which it meanders about from its streamlined trajectory depends upon what is the time. It depends upon the square root of the time. Okay. So essentially, if it meanders and then hits across the post, that you see the man going and hitting across the post, that's another way of capturing. So essentially, you have few ways of capturing. One, the particle hits the fiber. Second, the particle has an inertia, so cannot follow the streamlines and hence overshoots and hits the fiber. The third is basically if you have where there is a Brownian diffusion and this randomness causes the particle to take it to the fiber and it collides with the fiber. And in all these chances, as soon as you hit the fiber, there is a probability, finite probability, that you will be stuck to the fiber. Not every instance of hitting will actually cause you sticking, but there is a chance that you will stick to the fiber. Okay. Now, this is the problem, that you have one length scale in your problem and there is other length scale. Because of your breathing, you want this length scale, which is the distance between the fibers, to be large. And this is the other length scale, which is the particle is small. So essentially, without any, if it did not have anything else and it was a straight trajectory, then this particle would have gone through. But since there is this problems of inertia, temperature, Brownian diffusion, there is an effective size which grows in. So essentially, this particle is much bigger than what a bare particle would look like. And this particle now has a chance that it will hit the walls of your fiber. And if it hits the walls of your fiber, that's what the filtration works. But sometimes this is not enough. And when it's not enough, then you're trying to put in electrostatics. And you know this what happens is when you rub your comb with on your hair, it tends to pull particles from very far off distances. Okay. And because it tends to put in particles from very far off distances, then effectively this scale of the particle, effective length scale of the particle now becomes very, very large. So this particle now gets stuck to the fiber, though the gap between the fibers is very large. So this allows you breathability. This is what the N95 masks do. The N95 mask provides you with breathability, but puts in a lot of electrostatics in it so that the particles are attracted by electrostatic interactions. However, when you breathe out, then typically pathogens, which are charged particles, the viruses are charged particles, are usually in some sort of a solvent. It's in a spit. And what solvents do is basically it screens your charges. So essentially, you often see these droplets to be not electrically charged as you spit it from your mouth. But if you have gradients of electric fields, then even neutral objects can have. And essentially, because your fibers and these fibers do not give you homogeneous electric field, and this can give you gradients in electric field, means spatially varying electric fields. These spatially varying electric fields can act on electrically neutral objects also. And because they can act on electrically neutral objects, they can attract electrically neutral objects to your surfaces and then get trapped again. Okay, so you don't always need electrostatics to work. You don't always need a charged object. You can also have a neutral object but have a spatially varying electric field. Okay, so this is what Arnab talked to you about, the cloth mask and the N95 and the others. And Arnab, would you now talk them a bit over? Okay, fine. So let me do this. So the N95, if you decode the name, the N starts from the non-oil resistant, and 95% mask filtration of the 300 nanometer particles. Now you would say that in all of this, where did suddenly this number 300 nanometer come from? This looks like some kind of an arbitrary choice of a number. So let me get to this particular plot, that you have this N95 mask, which is essentially you have two layers of mechanical filters and you have an electrostatic layer in the middle, and it's kind of filtering everything. And you think that this filters everything which is beyond the 300 nanometer size particles, and so essentially it's good for you. So let me look at first, what do you want to filter? What you want to filter is various things. You could want to filter pollen grains, which is roughly 10 micrometers and above. You could want to filter bacteria, which is 300 nanometers and above. But you could also want to filter viruses, which is about 20 nanometers to 300 nanometers. Now, for this COVID case, you realize that if you really wanted to filter bare viruses, then N95 mask is of no good use, because an N95 mask does not really trap in really tiny particles. So what does it trap? It traps actually droplets that you actually exit from your mouth. Okay, so if there is a bare virus which is going around, an N95 mask is not good enough to basically block it. So if, however, if you are diseased, and if you are coughing, and if your cough is laden with these pathogens, and if the droplet size of your cough is larger than 300 nanometers, then an N95 mask is very good. Now, if you were to do sizes which is 1 micron and above, then a mechanical filtration would work for you. However, if you want to do sizes which is 1 micron and lower than this, then you need the mechanical filtration and electrical filtration together. And this is where the N95 mask comes in. So if you are trying to think about sizes that you want to filter, which is larger than 1 micron, then a mechanical filtration is good enough for you. If you're thinking about filtration of particles which are below 1 micron in size, then because of the questions of breathability, you want electrical filtration also to play a role. So you want electrical filtration, that means N95 masks to be effective for sizes about 100 nanometers and above. But if you are in sizes of say few microns and above, then a mechanical filtration should also work for you. I mean, these masks should also work for you. Okay. So since this whole thing is via droplets, it's good to look at what is the droplet size distribution. Now, want to think about why do you get a droplet size distribution? You know, why don't you just spit like a big drop? Why do you get these tiny droplets in your picture? The reason that you get it is because what happens is that your respiratory tracts are laden with some mucous membranes at its walls. Suppose you ingest something which your body doesn't like, then it goes in and gets trapped on this mucous membrane. It's like a sticky layer, so it goes and gets stuck there. Now you get the moment you get it, you get some kind of an allergic reaction. So your brain tells you that, you know, I'm going to let me throw a gust of air by motion of my diaphragm, and this gust of air should dislodge my particles. So as soon as you cough, there's a gust of air that comes out, and this dislodges the particle. And this act of dislodging the particle also creates these small droplets. And this instability, this happens via fluid dynamic instability, which is called the Kelvin-Helmholtz instability. Let me explain to you what it is. So think about this: that this is the wall of your breathing tube. This is basically the mucus layer, and this is the gust of air which is moving across. Now, for some reason, if you get to have a little bit of a disturbance up there like this, then because the air is faster here, then the pressure is lower here. This is almost like Bernoulli principle. This is why the planes actually get a lift. So you get structures which are like this. So thing here is the pressure is lower, so basically it goes up. Here the pressure is high because the velocity is low. The pressure is high, so basically this thing goes down. So essentially any wave, any disturbance, height disturbance on the mucous membrane now starts to grow. And then because there is this, if it grows too much and there is a shear layer over it because there's a flow coming over it, then this tends to break off into small droplets. This is a thing which you don't only see in coughs, but you also see in nature. For example, these kind of clouds that you see is also because there is an air which is, there's a wind which is moving across and causes a drag across a shear boundary layer from the surface and causes this instabilities which is known as the Kelvin-Helmholtz instability. This Kelvin-Helmholtz instability is what gives you the droplets. But what is the size distribution of these droplets? Because this is important for you to know what sizes should you want to filter. Now, this is one of the most controversial things in literature. Most people would tell you that this data, what is the size distribution, depends upon how you are measuring the size distribution. For some measurements which are very sensitive, these are based on light scattering measurements, you see lots of these tiny droplets that you have at scales which are less than a micron. And then you have these large size droplets, which is tens of microns to 1 millimeters. These tens of microns to 1 millimeters are the droplets The ones that you have these smaller droplets are usually called as aerosols. These are the ones that kind of hover in the air. And it's the general belief that when you transmit diseases, these are the droplets which matter for you. So essentially, if you look at these droplets, then these droplets are in a scale larger than microns. And if that's the scale which is larger than microns, then there is no need for you to use an N95 mask. These N95 masks are usually useful for people who are in close proximity to diseased people. And as a result, in the air around about them, there are lots of these tiny droplets. So, you over time, if you keep on ingesting a lot of these tiny droplets, then you have a chance of getting the disease yourself. There's also the problem, for example, if you're in a Mumbai local, for example, if you have a lot of people together, then though you may not be throwing out large droplets, but just by the process of breathing, if everybody is contributing to a large amount of these small aerosols in a very small environment, then you basically crank up the total number of droplets that is in a small area, and hence your chance of getting disease increases. This also happens when you share a Uber drive or a taxi with somebody who is diseased. So a close proximity with a person in a closed environment, that's the reason why you sometimes get this disease, even if you are not in the range of a spit. Okay. The size distribution is also not universal because it depends upon various things. For example, it depends upon what language you're speaking. Some languages have this thing of throwing out a lot of sounds, and whenever you make that sound, you tend to throw out lots of droplets. Some languages are soft on it. Your oral hygiene matters. For example, people who eat a lot of pan masala and things like that, they tend to salivate a lot, and when they talk, they essentially throw a lot of these droplets out. So essentially, a lot of these parameters matter, and there's not much of data, at least in the Indian context, about what are the droplet size distribution, what is the size that we should be worried about. But the essence is this, probably, that for a general public, you probably don't need very fine size droplets. It will actually err on larger size droplets. So essentially, keeping your mouth always covered with handkerchiefs or with at least surgical masks will actually help you. Now, there is also a problem with N95 masks, and the problem is this: because this based on electrostatics, and if you're breathing through these N95 masks, then over time you basically gather dust on these fibers, and if you gather dust on these fibers, then essentially the efficiency decreases because electrostatics decreases. So you need to sanitize this masks, and if you sanitize this mask, there are not many protocols which would keep the charge intact. Most protocols actually cause deterioration of the charge. If the charge deteriorates, then basically your mask doesn't work as well as it would, the N95 mask. Moreover, when you're wearing the mask, you're basically, the environment becomes very humid because you have a lot of humidity. Humidity is typically detrimental to charges. You know very well that electrostatics, this comb experiment, works very well when you are in a winter. When you are in a rainy season, then try doing a comb experiment. It won't work that very well because there's a lot of free water molecules round about. These little droplets of water molecules, they will try to take away all the charges that electrostatics can have. So essentially, this is one reason why you cannot wear a mask for N95 mask. If you're wearing an N95 mask for a very long period of time. So coming back to the story of this, how did we make about mask tester? And these are commercial mask testers that you can have, and these are typically priced at 20 lakhs and onwards. And what it basically does, in any commercial mask tester would do, is you would have a pump which would basically draw your gas through it, and this is the air which has these particles in it. And then you count how many particles are there in the flow. So you put a mask and count how many particles in a flow. Then you remove the mask, count how many particles are in the flow, and take the ratio of the two. That's how you know the filtration of the particles. And how does it work? It's because you have a laser. The laser scatters, and all of these things work on this principle that this is a single scattering event. Since the scattering of this the particle scattering are much larger than the wavelength of the light. The wavelength of the light is roughly about a half a micron, which is 500 nanometers. The particles that are scattering is from the scale of about 500, 300 nanometers to onwards. this is not the conventional scattering. This is something which is called the Mie scattering. And what happens is, if you are putting a detector at an angle, the intensity of the light that the detector sees crucially depends upon what is the size of the particle. So for example, most of these scatterers particle, if it's a bigger size particle, it will scatter in the forward direction. So essentially the little light will go here. On the other hand, if you have a kind of a spherical particle up here, a small size particle, then a lot of light will go in this direction. So depending upon this, you can actually find out what is the size of this of the particle that is scattering from the laser. That's how the particle counters actually work. This scattering is very different from the Rayleigh scattering, which one usually sees when the sun is setting or why the sky is blue. Remember, in the Rayleigh scattering, your particles are scattered by these water molecules and gas molecules, and their scale is much, much smaller than that of the wavelength of the light. So they are in, say, sub-nanometer scale. The wavelength of the light is 500 nanometer scale. In this particular instance, you are working with a scale, that means the scatterers are of the scale of either the wavelength of the light, comparable to the wavelength of the light, or larger than that. Okay, this is an example of what the scattering would be. This is a log scale. Log scale means like this is 10 to the power minus 4, this is 1, this is 10. You know, what I've done is basically, because the intensity varies by a lot, then I've actually plotted in a different way. It's called a logarithmic way. And if it is a 0.1 particle which is scattering, and what you can see here is a polar plot. What it tells you is this is the direction in which the light comes, and this is, if I put this, the angular distribution, and you can see the angular distribution is symmetric, which would mean basically that very tiny particles have symmetric distribution of your scattering. So it doesn't matter which direction you see, this roughly gives you the same value. The moment you go to larger size particle, this becomes anisotropic in nature. So you basically have lobes in this. So essentially, more scattering is in this direction, lesser scattering in that direction. So if you put a detector at 60-degree angle, you will see lesser signal than if you had put the detector in 0-degree angle. So essentially, 0-degree would be the forward scattering direction. If you have a still larger particle, you can see that the distribution is still more anisotropic. Most of the scattering happens in the forward direction. Now, in a commercial thing, this particular way of measuring the particle size through Mie scattering is also there. But these particle detectors, scatterers themselves are not very expensive. What is expensive is basically what goes inside the other part of the equipment, that is the pump, the aerosol generators, and things like that. So effectively, a lighthouse, which is what Arnab talked to you about, which is basically an equipment which is you in the clean room, which sucks in a particles. Essentially, what you do is you suck in the particle, and you put a filter, and you can count the particles at various channels. For example, you can count how many particles you have at 0.3 micron channels, 0.5 micron channels, 1 micron channels, 2.5 and 10 micron channels. So all of these tells you at various channels how many particles you have. Now, once you've got this number, then you can remove the filter. And then you see what is the ambient air counts of these particles that you have, take a ratio of them, and then that gives you the efficiency of the mask. So if you look at only the 0.3 micron channel, because that's the channel which an N95 mask would talk about. So whenever we talk about filtration efficiencies, we will talk about the 0.3 micron channel, because these are the tiniest particles which I can detect. Obviously, this lighthouse device is not something which everybody can have access to. So we replaced it with the plant tower chip, which is about few thousands of rupees in price. And effectively, this plant tower chip also does the same thing, except that if it does not count, the absolute numbers are not that great. But since you're taking ratios, you're not worried about the actual numbers. That's what our setup looks like. This is what our face is. Our face is a sphere, which is a ball, which Arnab got from his Chai and Y. So we actually stick our mask onto this ball. You have a vacuum pump through which we drag this air through. There is an air which comes in from here. There's a flow meter which tells you how much flow is happening. There's a differential pressure gauge, which means what is the pressure drop across your filter. This is the mask. This tells you how breathable your mask is. And all of this air passes through a plant tower chip, which tells you what are the particle counts that you have in your system. So, so there's a joke, you know, that that a theoretical physicist, or actually a physicist, has nothing to do with theoretical physicists. Typically, we simplify things. We convert our cows. If there is a problem of a cow not giving a milk, we find a solution of it, thinking that the cow is sphere, and then we ignore all the gravity effects of it, and then we also say that, why not have the cow in the vacuum, and if we put the cow in the vacuum, we can solve this problem. Unfortunately, if our face was that of a cow, that means of a sphere, it would be good, because on a sphere you can actually place a cone very well, but a face is not that of a sphere, and a face is positively, negatively, and zero curved surfaces, and as a result, it's not very easy to fit a mask onto it. So that's a negatively curved surface. That's your potato chip, which is a negatively curved surface. So in one direction, the curvature is in this way. The other direction, the curvature is in this direction. Okay, so that's a negatively curved surface. A flat sheet of paper is a zero curvature surface. A sphere is a positively curved surface. Okay? And your face is a combination of it. At parts, it's positively, at parts, negatively, and at parts, for example, this is zero curvature surfaces. Okay, this could be negatively curved surfaces. This chicks could be somewhere here, could be positively curved surfaces. So it's basically difficult to get a mask to fit onto your face. And people worry about how to fit masks onto your face. And one of the things that, many of these N95 masks cost you a lot, and some companies get it right and some companies don't get it right, is basically how to fit your mask onto your face, which is not a very nice surface to get something to fit onto. Okay, so what you do is, to get the fit onto this mask, we often have to tape it. And this taping is very important, because if we don't tape it, then there's a lot of leakage that happens to the sides. And we figured out, even when you put the mask onto your face, then there's a lot of leakage which happens from your sides, and that basically deteriorates your filtering efficiencies. Arnab, can you continue with the next of it? Okay. So that's what you have. You have a system where you have a mask. So you put the mask. You don't put the mask on it. You have some counts in your channel, which is about 0.3 micrometer channel. That you have some counts on it. The moment you put in a mask, your counts drop in, and by changing by looking at the ratio of what was the counts in absence of the mask and in presence of the mask, you can basically tell what is the efficiency of this mask. Okay. So if you are looking at a 0.3 micrometer channel counts, and say, for example, your various masks, say your mask 1 has 68% mask filtration efficiency. This is some kind of a mask which is not an N95 mask. Mask 3 has 96%, which is probably some kind of a mask which is like this, which has a larger efficiency of filtration. So this is how you basically measure the filtration efficiencies of these masks. Okay, what is the importance of getting a tight fit? So, for example, if you don't get your fit right, for example, suppose I don't tape it at the side. So you wear this mask, but you have not taped the mask actually well up here, or the mask is not sitting very well onto your face. Then you can see that if the taping is not right, or the fit of your fitting is not right, you get a 71%. An N95 mask will be as good as a N71 kind of a mask. It's only when you tape it properly, or only when the mask sits very well to your face, do you get an N95.4 efficiency. Okay, and how do you get an efficient mask fit? Well, there are various ways of getting it. One is to know how to use an N95 mask, and for that you probably are trained how to use an N95 mask. So if you just go to the market and just buy one N95 mask, it's highly likely that you won't know how exactly to put on an N95 mask on your face. But there's something else that we came up with. Actually, this was from an idea which got from the fixmask.com, that you can actually put a gasket onto your face. And this is what happens when you put a gasket onto your face. And let me see if I can get you the video running. So that's Satyanu, who is trying to show you how you can actually use ordinary handkerchief. So he wears a handkerchief up there. And this mask, obviously, if you look at it, this part of his face is open, so there will be a lot of leakages from here. And then Satyanu does this little small simple thing, and he holds this thing up here. Well, he misses the first time. It's clumsy. And then he gets the next time right. So this kind of a small gadget would be able to get you very high efficiencies even out of handkerchiefs. What it does, it actually gives you a very nice protection. You see, this part is now closed down. This part is closed down. It's not even uncomfortable to wear because you are tying it from the back, so you can actually control the amount of comfort level that you have. Okay, and if you instead of taping, if you actually go and put this masks onto your balls, you can see that you can actually drive these things with a black strap. You can get something which is 67% to about 93%. So a lot of this filtration actually depends upon how well you have actually put this mask onto your face. Because if you put this mask onto your face and you have these things open, then this is the place from which there will be large blocks of large air which will come in, and that will what will cause your efficiency to drop. Even with an N95 mask, if you don't wear it very well, and if you leave it gaps open here, the same thing will happen. So your N95 mask will be as good as your N73 or N50 masks. So comes Act 2. So this is where I have a long-term collaborator of mine who was claimed to fame is because of quasi crystals, and he co-wrote the paper for which the Nobel Prize was given. Um, Dove and I were working on totally something very different, and we usually talk every day on Skype for about an hour or so. And for some weird reason, Dove had this idea that he said, Shankar, can you actually, we were talking about masks just because everybody is talking about masks by this time, and this is 18th April. That you tell me that the masks are not to be, decontamination takes away the charges. And we know that if you put in batteries, why can't you charge a mask with a battery? Okay. How do you charge the mask with a battery? The idea is, well, you take a Duracell, put it to a mask, and it should get charged. But the question is, why should it get charged, and how should it get charged? Okay, so we've spent the next few days worrying about how can you use a portable battery to recharge your mask, and this is how you can get it done. The reason that the masks have charges on them is because they are called as electrets. Electrets are analogs of what you know as magnets in your system. Magnets are something which have a permanent magnetization, so it attracts another iron filing to it. Electrets are something which can attract some polarizable object to it. Now, typically, if you have electrets, they are dipoles in nature. That means there is some combination of plus and minuses which are likely separated from each other, but they're randomly oriented. So essentially, the net dipole moment in your system is zero. So one way of getting these electrets to become net polarized, that means have one side positive and one side negative, is to put it to a field, high field, but also lower down the viscosity of it. So essentially, you take an electret, wax is a good electret, for example, and then what you do is you melt the wax. And if you melt the wax and then put an electric field, then each of these molecules which are acting like a dipole can actually reorient itself, and they reorient in the direction of the field, and that gives you the net dipole moment in it. Now what you do is have the electric field on, switch off your heater in the system actually freezes, and you get the total dipole moment in your system. Okay, that's how your electrets work. There's other ways of getting a charge. For example, rubbing gives you charge. There's this electric charging. But the problem with rubbing that gives you charging is it also loses the charge. This you know very well. If you take your comb, it works for about a few minutes or maybe at the best 10 minutes, but then you lose the charge because those free radicals somehow pick up the charge from the environment and they're passivated, right? So essentially that doesn't work. These are kind of things which work better, but these are things which work only when you can actually increase the temperature and then polarize the whole object. However, even this tend to get lost in time, and if this gets lost in time, it's very difficult to recharge the masks because you can't really heat up a mask and then apply an electric field. But you can do something else. Most masks are not, these electrets are in this particular system are polypropylene. Polypropylene is known because these are easy to make, and these are melt blown fibers. What you do is basically you take some polypropylene, you melt them, and you bring them to a nozzle and blow hot air through it. And as you blow hot air through it, you spin out little small fibers through it. This is like sugar candy, the way the sugar candy works, it exactly works the same way. And then you have a drum which basically is collecting all of your fibers. And these are non-woven fibers because nobody is stitching them. So they collect in some kind of a random mesh. And this is what the polypropylene fiber does. But polypropylene has this very interesting property that its electrical conductivity depends upon the electric field that you have applied. So what is the conductivity? It means how easily the charges can move in and out of a system. So if you apply a very high electric field to your polypropylene, then essentially all of these polypropylene fibers then becomes conducting. So if you have a conducting material, then you can actually put in your charges. So for example, if I connect a metal to a battery, then all the charges of the battery potential will actually move on to the metal. Well, if the circuit is not complete, it won't flow back to the other end, but essentially that will be the same potential. So you can inject charges into a metal. You can't inject charges into an insulator. Okay. So you apply a high field. In a high electric field, you can inject the charges into your system. Now what you do is you switch off the field. As soon as you switch off the field, the mobility drops. If the mobility drops, then those charge carriers are basically trapped in your polypropylene fibers, and that gives you the charge on the system. Okay? So we can show you an experiment in which that's how we find out. First, we have to find out that you know how much charge that you have in your system. Most of these masks that you have, the better the mask is, usually has more charges on it. So you do it by measuring the charge. So if you have so for example, there's a company which has a 9 nanocoulombs of charge on its surface. And the way we do it is by measuring the charge by connecting an electrometer across to it. Has the highest amount of efficiency. The smaller the charge that you have on your mask, the lesser is the efficiency. If you want to recharge, what you do is you basically sandwich this to this mask between two electrodes, and you have a positive electrode and a ground electrode, and you apply an electric field. In this case, we apply about a kilovolt of it. Keep it for about 10, 15, 20 minutes, and you can recharge your mask. And the recharging time depends upon how much. The recharging time depends upon how much you have actually charged it for. Does find you can recharge your mask. Does your recharging improves the filtration efficiency? And yes, it does. And you can see that when you steam expose, this is a way of decontamination. You are decontaminating your mask. The N95 mask falls to about 77%. And if you decontaminate your masks and then recharge it, then the mask efficiency goes from 77% to about 86%. Over time, this actually discharges, like any electrostatic mask, they will discharge. So essentially what you get to be at 88%, you can discharge it and take it to about 70% with time. So in about, say, a few hours, it will actually drop to about 70%. And so to circumvent it, you can do something else. You can constantly charge it. This is a battery operated mask. And I'll tell you what it is by actually showing you a quick video. So this is what battery operated mask would be looking like. So what you do here is you put in your fibers. This is your fibers between two metal meshes, connect it to a voltage multiplier and add a 4-volt battery to it. And the way you make this mask is first you take a metal mesh. This is your metal mesh. This is the other metal mesh. And this is through which you apply the electric fields in it. You put a gasket because you don't want the metal meshes to short and then have electrocuted with each other. Then you put your fiber structure. This is basically cut from N95 masks. You put another gasket and you close down the whole thing. And with another gasket, you close it down. And then you can see that this particular kind of a mask, which is battery operated with a 4-volt, typically with a filled on, has about an efficiency of 96%. So Arnab, that's your act.
Okay, so Shankar has told us all about how masks work, the physics, how you can recharge it, etc. And the main thing is masks, actually, I'm going to look at a little bit more practical issues. Masks do work, and there is no dearth of studies right now which say that, for the general public, even a simple cloth mask is actually very useful. Masks work. They are very useful in preventing the spread, sort of reducing the probability of spread of diseases like COVID-19. We can send you these links later if you'd like. Also, I mean, those were some general work for various things. Even recently for COVID-19, there have been lots of studies, both simulation studies, modeling studies that show that these masks are very effective. So for example, people have shown that depending on the fraction, so what you see on the x-axis is the fraction of the population that is wearing a mask, and on the y-axis is this famous number now that probably people have heard of in relation to COVID, which is R0 or R0, which is one person infects how many more people. If that R0 number can be brought less than 1, then on the average, you're infecting less than one more people, so the disease cannot spread. And people have shown that just by using masks, if everybody, if more than sort of 75% of the population wore masks, and they wore sort of, even a 75% efficient mask, you would very quickly, or even a 50% efficient mask, if the population wore it, you very quickly reduce this R naught number significantly. Of course, you must be a little wary when you read papers. In today's world, people are writing papers on COVID, and they are given the interest in the field. They are all coming out very quickly. So of course, here's one with synthetic control. People have done it. But yes, this is the paper I wanted you to be sort of wary about. Many people have claimed many things, and this one which it was actually said that airborne transmission, aerosol transmission could be important. Earlier, people were saying droplet transmission is important. Now, of course, remember that you have a Nobel laureate on your author list. The paper does make one very, very important point in the abstract. And I think, of course, it says that masks are the way to reduce the spread of COVID. But at the end, it says that sound science is essential for decision making in current and future public health pandemics. And I think that is really important. I think it's important that we follow the science and not be guided by other things. But do remember that not everybody agrees with this aerosol transmission picture that this paper tried to present. Anyway, even the WHO agrees now. Earlier, the WHO did some flip-flops between whether people should wear masks or not wear masks. Even they say that, yes, wear a mask, it's good. In fact, they put out a video about, what mask should people use, who should use what kind of masks. I was very happy to see that they recommend cloth masks, but, I was a little surprised at the kind of crowd they put over here. This office almost looks like a Mumbai local to me. But even in crowded environments, a mask will really, really help you. Anyway, but the important thing is, and this is something which I find everywhere, that most people do not wear a mask correctly. If you are watching this talk, the one thing which you would like to take home is that you can have the best mask, but if that mask is not covering your nose and mouth, it's useless, right? You do not have to take your mask off if you're making a phone call or speaking. You have to cover your nose. You have to try and get a good fit around the thing, not with big leaks at the side. But people are very, very careless with the way they actually wear a mask, and that then defeats the purpose of having a mask. There's no point, spending a lot of money on a N95 mask and then not having it cover your nose. So do check that out. Okay. By the way, there are some masks which have valves, and here is one. This is an N95 mask which has this little valve. These masks are actually not meant for medical use at all. These masks were designed to be used in dusty environments. This valve is meant to ease breathing. It's an exhalation valve. It allows the air that you breathe out to go out without any being blocked by the layer of the material of the mask, which makes breathing easier. But this means this is like a open path for things going out. So yes, this mask will filter particles coming in, but one idea of the mask was to prevent, if somebody is infected, to prevent their own droplets going out, and this will not do that. Okay, so if you're wearing this mask, I mean, if you find somebody wearing this mask, stay away from them, because their particles are not being blocked by this mask. This is meant for dusty environments, mines, etc. In some places where you have no option, what people do is cover this with another thin thing to prevent particles going out. That works, but please beware of masks with valves. They are not effective. There are a lot of articles on this now saying that these masks can actually do more harm than good. Also, one must be careful, and we have done some measurements which actually show that because this valve has a little rubber gasket, and especially in the humid conditions we have here, rubber is a sticky material. Dust particles will stick to it, and once it sticks, the material of the mask is fine, but the leakage after some time will be through the valve, and that is not desirable. But the other thing, which is unfortunately spreading a lot, I mean, given this COVID pandemic, everybody is trying to make masks. Okay, and in India, if you want to make a surgical mask is something like this. The material of the mask is tested by the South Indian Textile Research Association, CITRA. If you make N95 masks, the material is tested by the DRDO. But both of these organizations, they just test the material. They don't test the whole mask as such. At least CITRA doesn't. And wearability, etc., is a completely different thing. But there are lots of masks which will claim that they have been tested and or they offer some fantastic filtration, but will say nothing on breathability. Remember that I can take a stainless steel vati and put it across my nose. That's not going to allow any particle through it, but I can't breathe through it. Well, of course, you could be like some guy in Pune who made a gold mask and then drilled holes in it. Of course, that's a fantastic mask if you're going to drill holes in it. But you have a lot of masks which will claim that they are, for example, approved or tested by Citra or something, but they are not really 90. A good 90 N95 will always be better than this. But we measure some of these masks which claim to be 95, but they're hardly 85%. And Citra themselves have put out an ad, and so has DRDO, saying that you cannot say certified by Citra. So if a mask is going to say certified by Citra or approved by DRDO, please be very careful. People are not even supposed to do that. The agencies have put out disclaimers saying that you cannot put it out on the mask. So don't go by these hype things, right? So the other big confusion is, as I said in the beginning, these masks are tested at 3 microns. The N95 masks are tested at 10 times smaller, 0.3 microns. So many times the advertisements will actually measure bacterial filtration efficiency at 3 microns, but then call it an N95, and that's actually very misleading. So please be careful, read the fine print carefully. Well, one question is, okay, not everybody needs an N95, but how good are these masks? Well, there is a huge variability. You must ensure that you have what is called a 3-ply mask, okay? Now, I am going to, a 3-ply mask can often filter 65, 75% efficiency you can get with these masks on your face, which are very good. Your standard cloth mask, 2 or 3 layers of cloth, will also give you a similar efficiency. But sometimes these masks are only 2-ply masks, and I'm going to sacrifice one of these masks. So I'm just going to cut this. Okay. If you cut the mask, you will see that this mask has only 2 layers. There are only 2 layers. A good mask, and even the WHO recommends, a good mask should have at least 3 layers. So please make sure that the mask that you get, if you're going to get these masks, has at least 3 layers, what is called a 3-ply mask, not a 2-ply mask. This hardly filters 25 to 30%, as you see in the middle over here. Okay. The last part is a little bit more serious. And now we want, healthcare workers, there's a big shortage of these N95 masks. Can you actually decontaminate and reuse these things? Now, the biologists know very well how to kill viruses. They will die with heat. They will die with, ultraviolet light. There are many ways you can kill viruses. The question is, when you do that, do you impact the filtration efficiency or the breathability of the mask? And that's something which we set out to check. And again, lots and lots of claims you have to read very carefully. In the medical terms, things like decontamination and sterilization and disinfection are very different. Sterilization actually means you're killing 99.999% of your bugs. Okay, decontamination, you need only 99.9. So, people, even with UV light, people sell sterilization boxes, but they're probably not doing any sterilization in that at all. So, this N95decon.org community, they've put out very, very useful guidelines on what it is. And often the limitation in reusing the mask is not the material. The material is fine. The straps come off very easily. If the strap is off, you can't use it. Okay, so you have to be careful that it's not just the mask, or the mask material might filter well, but it can get deformed and not fit on your face very well. So there are a lot of considerations to take into account. First thing, let me tell you what doesn't work. You can wash your hands in soap and water, 20 seconds kills COVID. Alcohol, rub your hands, 70% alcohol kills COVID, but they also kill the mask, because as Shankar had said, it's all about charge. And alcohol or washing your masks or something is most likely going to remove the charges from this intermediate layer, the polypropylene layer, and hence decrease the filtration efficiency, right? Similarly, bleach, yes, it'll work, but apart from removing the charge because it's a liquid, the traces, if they're left behind, are not very good. Similarly, gamma rays don't work. Sunlight is only what is called UVA. It's not short wavelength enough to actually kill viruses. You'll kill some because you heat up the mask in the sun. That's slightly different, but just the UVA component doesn't work. What works? There are some things people have shown with hydrogen peroxide vapor, but these are usually industrial, large-scale things. Just keeping the mask out, time. If you leave the masks, people have measured the SARS-CoV-2 virus. How long does it stay active on various surfaces? Paper, plastic, metal, glass, mask material. And if you leave it out for more than 5 to 7 days, there's no virus left on it. It's automatically by itself got inactivated, and that is the easiest way to do it. Of course, you can heat it, especially moist heat, or treat it with enough dose and intensity of UV light. And in the Indian context, leaving it out for a while or just heat is probably the easiest thing to do. And this is something we worked on quite a bit. With Tata Memorial Hospital, what we did at TIFR was we set up a little thing to check how, in a small oven, how the masks behave when you heat them. We found that some of these masks, you can heat it for an hour, 3 or 4 times, and there's no change in the filtration efficiency or the fit of the mask. They remain the same. And then I'm happy to say that this has been now deployed at Tata Memorial Hospital, and hopefully they will use this to extend the life of thousands of masks and hence save these scarce resources that they have. So with that, I think it's time to wrap up and take questions. So masks are actually very, very useful. As you've learned, we can filter them either by just trapping particles that hit it or are diverted to it somehow, or through electrostatic charge get attracted to the fibers. And it's one very easy way of trying to help stop this explosion in growth in the spread of COVID. For most of us, a cloth mask or a surgical mask is more than enough. The N95s are special for healthcare workers, and the most important thing is it has to fit well. There's no point having the best mask but not having it fit on your face well. We can decontaminate these masks, but we have to be very careful with it. And Shankar and I and all of the students we've worked with and our collaborators, we've had a lot of fun learning all exciting things about masks. It's something that we knew nothing about literally when we started this 3 months back. And I hope we could share some of the excitement that we felt and some of our journey with you. And we will be very happy to take questions. Now, I know that there are questions coming in on Facebook and on the YouTube channel. I've actually made a note of them. So Shankar, why don't I get my laptop and so let's look at the questions. I'll try and come somewhere behind you so I can sit there well. Okay, so all right. So there's a question on YouTube which says if you can of course smell things through the mask. Does that mean viruses will get in and smell things through the mask?
Well, typically the molecules which give you the smell are of the size of few nanometers, no, smaller or slightly of that order. Viruses are 20 nanometers and above. Anyway, none of these masks are supposed to block your viruses. If they are just bare viruses, they are supposed to block droplets. Bare viruses, if they were to be in the air, suppose, let's assume this scenario. You have a droplet which contains some amount of viruses, and the droplet evaporates. Obviously, the water can evaporate, your virus is not going to evaporate, right? So that's in the air. If you're going to ingest that amount of virus, then it's unlikely that most of the masks will stop it. So yeah, so that's the answer.
So in summary, the molecules that we smell are way too small. There are a few nanometers. A virus is at least typically 20 or 100 times bigger than that. The SARS-CoV-2 virus is 120 nanometers or so. So you will smell. None of these masks will stop you from smelling odors in the environment. They might be blocking. It's a very different size that's at play. Okay. Vivek wants to know that droplet sizes could be less than 0.3 microns. Can N95 stop them?
No, not so. The way it works is this: N95 has 95% of cutoff at 0.3 micron particles. So it means that if you go to lower sizes, then some amount of the droplets will get blocked. So if you're at 100 nanometers, your efficiency will drop. I don't know what number, but it will drop, maybe N70.
But isn't it true that 300 is about the most difficult to filter, and hence?
No, I don't think there is anything to do with the most difficult to filter. You will have smaller size. See, there's a question of trade-off between what is filtration and what is breathability. It turns out that probably is a sweet spot in which you can have the best of filtration is about 300 and as well have breathability. Because if you want to go any lower than that, the problem with all of these things are droplets. When you have droplets are not electrostat. They are not charged. So essentially, you don't have the monopole term of your electric field. So that means it's not like some plus charge attracting some minus charge. So you're doing working with something which is slightly weaker in nature, which is to do with gradients. That means spatial varying changes. So your efficiency goes down a bit.
So actually, this is related to another question. There's a request if you could please revisit this electric phoresis mechanism and how this works, how the charge-based trapping happens. So maybe you could just go back to the slides and explain that little thing again. That even if it's not charged, it can get attracted to a mask.
Okay. So the idea was this, right? So the idea was this, that you want large pores to trap very small particles. Now, how do you do that? You basically want to have long range interaction. That means, you want to catch hold from somebody from very far off distances and basically pull him towards you. The way you do it is by electric field, because electric field is 1 by r, so essentially has very long range interactions. So this is what you do with an electric field: charge it, have counter charges on the other surface, and attract. Unfortunately, most of your pathogens which have surface charges on them are also laden with this saliva, and their saliva has a lot of counter charges on them. The problem is, suppose you have a charged surface, but you have a lot of counter charges on them. I mean, a lot of free mobile charges in your solvent. Then suppose you have something which is positively charged, okay, and you have a sodium chloride solution which is coating it. Now, all the negative, the chlorine ions will come and sit close to the positively charged surface. So effectively, the positively charged surface will not be seen well from outside. This is called screening, electrostatic screening. So that's why the first term, that means a plus charge attracting a minus charge, or a minus charge attracting a plus charge, this doesn't work so well for your saliva droplets. What works otherwise is the next term in your problem. This is to say that your electric field, so when you have a droplet like this and you apply an electric field across, this droplet becomes polarizable. And then it tends to move in a direction so that it can minimize its electrostatic energy in the system. So remember that anyway, any time that you apply an electric field in the system, some amount of opposite field is generated inside the droplet. Okay. So that's the polarizability of your system. That's how polarizable your object is. This is a neutral object. Now, if you put a neutral object in a parallel electric field, like a capacitor, then this object is not going to have any motion. But however, if you put them in some gradients in an electric field, for example, this one is a gradient electric field. Suppose there was a pin up here, okay, and there's an extended electron on the other side. They will give you a gradient of the electric field, and depending on the polarizability, there will be a force acting on the whole object, which will depend upon how does this spatially varying electric field spatially varies. You think, why does this electric field spatially varies? Because every electron, every fiber doesn't have the same amount of charge. Even on a fiber, the charges are not same at every point. So essentially, even as you go along the length of the fiber, the electric field is a spatially varying quantity, and this spatial variation of the electric field induces a field on a neutral object also via the polarizability. So that's where the dielectrophoresis comes into picture. So this is the dielectrophoretic, because it's a dielectric object which is not a charged object but gets attracted by the electric field or moves into the electric field. It depends upon what is the gradient of the electric field.
Okay, there's a question that says, what is the best way to clean cloth masks at home? So maybe I can just take it from here. I hope you can hear me. That's fine. I think we maintain our little distance. For cloth masks like this one, the best thing to do is to just wash them like you would wash any cotton cloth, soap and water, put it in your laundry, let it dry. Okay, can you come closer? Another chair here. Okay, the question is, how do you wash a cloth mask at home? Well, as you would do with any other cotton cloth or t-shirt, you just put it in the laundry, wash it with standard detergent and water, a warm wash, and then hang it out to dry. In the monsoon, you're not going to be able to sun dry it. Sun drying would be easier. If you're really paranoid, you could iron it and make sure that's probably good enough. Just standard wash and dry for cloth masks is fine, absolutely fine. Let's see if we can get some more questions from here. Yeah.
Can you do the coin thing again?
Yes. Okay. There's a request to do the coin thing again because we forgot to turn the screen share off. So what we will do is I'll request Shankar to go to the board and do explain the multiple length scales in filtering once more. And this time we will make sure that you see the screen, full screen, and not the slide share. So let me do one thing. Let me just put screen sharing off for now and turn the camera around again. So Shankar, maybe you should just start all over again, and I will hold the camera more. Yeah, yeah. Okay.
So here is his argument that what you do is you take this is a filter, for example. So the filter has some length scale L, that's a pore size, and you have an object. Say this object's length scale is A. And if L, that means the pore, is smaller than my length of the object, then this will get blocked. And that's the whole idea of filtration. Now think of it that if you wanted to make a 2D filter, this is one dimensional problem. How would you go about doing it? The way you would have gone about doing it is basically take some sheet and punch holes into it. And then you would ask, well, you know what I'll do? I will find out the length scale of what is blocking. Okay, so this is so essentially, sorry, these are this is slightly different. So let me just do it again. So the point is here that what you have is you have fibers here. So you have fibers here. These are the fibers, and I have taken a cross section of it. And this is the empty space. This is the space through which actually your particles can go in. Okay, this open space, the space through which your particles can go in. Now you can ask this question: that what is the length scale now I should compare? Now it turns out that it's a little tricky question to think about. Now look at this. Look at this problem here. If these were the 3 fibers, take 3 straws. Okay, 3 whatever your cold drink straws, and you put them together, and then look at from the front on view of it. This is 1 straw, this is the second straw, this is the third straw, or these are the 3 coins. Each coin is of a radius A, diameter A. So there are 3 coins which are kissing each other. Okay, 3 points, and each have a diameter A. Now, because they are in the diameter A, the distance between them is 2A. Okay, this is 2A, so there is one length scale defined to it. One length scale defined with respect to that of the coins. But if you look at the scale which is inside here, it's difficult to find out what is the length scale associated with it. When I give you any space, suppose I give you like this, suppose I give you some space like that, and I tell you what is the length scale associated with it. Now the way you find out is you try to find out how many circles can I put it into it. So you start with a bigger circle. First you do it, you start with a big circle somewhere up here. Okay, you say, well, I can fit one big circle. Then you try and fit the next circle like this. Okay, there are these 2 circles can be fitted like this, or maybe 3 circles of this radius can be fitted up here. Then you try to fit smaller circles. Okay, that's how you find out what are the length scales. All of these length scales are basically there in your system. Now, if you look at this particular system, then you will find out that you can have smaller and smaller length scales associated in your system. So there are a large hierarchy of length scale associated with your system. What you need to now know is what is the largest. So essentially, if you have a length scale, say A, okay, this is the length scale which is the smallest length scale of my. Okay, let me say D. Say this is my. Say let D be the length scale of the particle that I want to now filter. Now it should turn out that the smallest length scale here should be greater than, should be smaller than the size of this particle that I want to filter. Because if this tiny length scale, then it will actually go through this smallest length scale up here. So this is why getting a filtration working is pretty difficult in actually even in 2D also. So that's the multiple length scale problem.
Okay.
Another question: how are the masks made to not discharge over time?
The masks do discharge over time, and that's one reason that you cannot use an N95 mask forever.
So the answer is masks do discharge over time. The masks do discharge over time. You cannot use it very long. Okay, let me see if there are other questions coming up here. I have a list.
Do we know of any material to which a virus or aerosol could easily bind?
So this is an interesting question because this turns out to be a point that do you want the fibers? Let's ask this question. Your aerosol is basically a drop. So your aerosol is one droplet and you have a fiber. And you want to ask this question, then mostly it will be a polypropylene fiber because that's the easiest material that you can have. You could ask this question that do you want smooth fibers or do you want rough fibers? Because typically you have very smooth fibers, but if you have very smooth fibers, then the droplet that sits onto it tends to actually move on the surface. So you can control the amount of adhesion that you can have to the surface by controlling the roughness of it and the wettability properties of the surface. So you, for example, do not want a surface which is very hydrophobic, for example, it will just drop off.
Okay, so let's look at Facebook. Shankar, this is for you probably. When will the battery operated mask be commercially available? How much is the cost of making it compared to a normal mask?
I don't think
do you think it's the best possible solution, etc., etc.
So battery operated masks, given that this pandemic situation is, I don't see it coming up in this COVID-19, but we have been trying with Technion to actually have this commercialized. There are two parts of it. One is to say that can I actually use electric field to actually recharge masks? Okay, and there are various other methods that we are coming up with recharging the masks. There are YouTube videos. We are in the process of posting how to do that at home. So those kinds of things will always be there. But in terms of the battery operated mask, I think this is a smart mask idea. So this will actually take some time.
Okay. Let's see. How can you tell if a surgical mask is 2-ply or 3-ply? A very simple thing, you cut the mask and you check how many layers you find in it. So you have to sacrifice one mask at least. Sometimes you can probably pull the 2 layers apart and see that yes, there is a 3rd layer in the middle. But I think the only short way of doing it is to cut it and to see it.
So the other good way of it also is to hold your mask in light. If you see all the light coming through, that means the photons are coming through it. So essentially, that's not a great mask.
So here's actually a very simple test for to do at home. Now most of us all have a mobile phone with a torch in it, and if you see this is a 2-ply mask, and here's your, I'm just going to hold it here. Look, you can see most of the light through this, right? Whereas if I take a 3-ply mask, which is a reasonably good 3-ply mask, this certainly blocks a lot more of the light compared to this one. Okay, and actually it's much easier if you do it with your eye. Your eye is much more sensitive. I mean, the camera is getting bleached out, so you really don't see the difference very much. But you can compare different masks very easily by just, at least for the cloth masks, by just looking at how much light from your cell phone torch or something is getting transmitted. That's one very easy way to check 2-ply, 3-ply, etc. Okay, other questions I had a list here. Okay. Do masks filter out any healthy things? I don't think so. I don't think there are healthy particles that we really breathe. I mean, most of the pollen and the dust and all is actually treated by our thing as an allergen. So I think it's probably not, there are no really healthy things getting filtered out by a mask. Okay. That was there. Let's see any other, nothing more on Facebook. And let's just check your YouTube stream once. Can we find the efficiency of homemade 3-cloth masks? Well, of course, we've done that. And a lot depends on whether it is an old banyan or an absolutely new one. And as Shankar said, remember, sometimes these old cloths are better because they are frayed and they have a lot more surface. In general, if you have 3 layers of typical t-shirt material, hosiery material, you will get an efficiency of 50-60% very easily. It could go all the way up to 70% also. Depends on the material, depends on the thickness of the layers. With everyone's banyan and t-shirt, it's going to be different, so it's really difficult to say handkerchief, whatever it is. But in general, they're all reasonably good for everyday use for general public. That's what I would try to say. Okay, so are there readily available gaskets for masks? I don't think so, but I am sure that there are many of these sites which have designs for how you use 3 rubber bands to make a gasket, or how you can cut out a gasket out of a piece of a rubber sheet, like an old glove or something. You can cut out a gasket from rubber, or you can just use 3 rubber bands or 4 rubber bands to make these little gaskets to seal a cloth mask on your face. Okay, any more questions? Doesn't look like any more questions. Remember, you can always write to us, outreach@tifr.res.in, and send us your questions. So at this point, I'd like to say thank you. So I hope Shankar and I could tell you a little bit of the work that we're doing, and a little bit take you into the world of masks. Thank you very much, and see you 2 weeks later again at yet another online Chai and Wai, until we are allowed to sort of really get back to our venues and interact with all of you in person. Till then, stay safe and wear a mask.